Hi, apa semua? Let's talk about robot arm kinematics. So, robot arm kinematics deals with the analytical study of robot arm motion without regard to the forces and/or moments that cause that motion. On the other hand, robot arm dynamics, which we'll be studying in the future, is concerned with finding the relationship between actuator forces and the motion of a robot arm, which means by using robot arm dynamics, we'll be able to compute robot arm angle, angular velocity, and angular acceleration values. This will be actuator forces. And the reverse is also true. So given some motion and some quantities or parameters, we'll be able to compute actuator forces that would cause that motion. In robot arm kinematics, we will be not considering the forces and moments, and it can be divided into forward kinematics and inverse kinematics. Let's say we are given a robot arm that looks like this, and it has several joints and links. Let's try to label them first. So this is joint 1, joint 2, joint 3, and joint 4. And this is called link number 1, link number 2, link number 3. And this will be theta 1, theta 2, theta 3, and theta 4. And we can see we have an end effector here. And on that end effector, we have a fixed coordinate frame. And let's call this coordinate frame as coordinate frame number 4. Hence, we will label the axis as x4, y4, and z4. So in forward arm kinematics, we'll be able to compute the position and orientation or the pose of the end effector given the angles and geometric link parameters. So given theta 1, theta 2, theta 3, and theta 4, and geometric link parameters, which basically define the position and orientation of one coordinate frame with respect to another, we will be able to compute the pose of the end effector, which simply reduces to the homogeneous transformation matrix T for 0. So 0 here will be referring to a reference coordinate frame that we have to attach to the base of the robot arm. So this is for arm kinematics. And inverse kinematics will be simply the reverse of that problem. So given the position and orientation or desired pose of the end effector, T for 0, and geometric link parameters, we will be able to compute the joint angles. So you'll be wondering, what are the application of forward kinematics and inverse kinematics? So with forward kinematics, if we know the minimum and maximum values of these angles, then you can compute what is the maximum area of your task space. So for example, if theta 1, the minimum value that can be produced by joint 1 is, let's say, minus 150 degrees, and the maximum angle of joint 1 is 150 degrees. And so given the minimum and maximum values of all these joint angles, then you'll be know what is the maximum area or position that this end effector can reach. So that is the application, one of the applications of forward kinematics. And for inverse kinematics, it seems to be more useful, because if you want to pick an object in a certain way, in a certain location and with a certain orientation of the end effector, then with inverse kinematics, we will be able to compute what is theta 1 up to theta 4 to produce that pose of the end effector. Let's recap on the homogeneous transformation matrices. We know if we have a coordinate frame A and a coordinate frame B. Let's say if I want to represent the pose of B with respect to A, then I have to compute the homogeneous transformation matrix TBA. So this matrix, which is a 4 by 4 matrix, it will represent the coordinate frame B with respect to coordinate frame A. Basically, it has 4 submatrices, and we know the last row is always 0, 0, 0, 1. So this 3 by 3 submatrix, it represents the rotation of coordinate frame B with respect to coordinate frame A, and this 3 by 1 column represents the position of the origin of B with respect to A. And if we want to map a position vector from one coordinate frame to another, then we have to use this equation. So we have to represent the position vector in homogeneous coordinates. So here we are mapping a position vector expressed in homogeneous coordinates from coordinate frame B to coordinate frame A. So these are expressed in homogeneous coordinates. And similarly, if I want to compute P tilde B, I need to use TAB. And we know from our previous lecture that this is simply TBA inverse. So given a homogeneous transformation matrix, we know that this part, this 3 by 1 column is really, this is XB, right, with respect to coordinate frame A. And similarly, the second column is the y-axis of coordinate frame B with respect to coordinate frame A, and the third column here is the z-axis of B with respect to coordinate frame A. So if we perform a purely rotational motion, or if we have rotated a coordinate frame, purely rotated without any translation, then we can use one of these 3 homogeneous transformation matrices. So if we have performed rotation about x-axis, then we have this. This is a slight abuse of notation, but I think you know what I mean. And if you have rotated a coordinate frame about y-axis, then this is the homogeneous transformation matrix representing that rotated coordinate frame. And finally, if we have rotated a coordinate frame about z-axis, the homogeneous transformation matrix would look like this. So by the way, c theta here is cos theta and s theta here is sine of theta. Okay. And if we have performed or translated a coordinate frame, purely translation without any rotation, then we have to use this to represent that motion or pose. So D here refers to a pure translation. So the rotation part will be identity matrix. So normally, in general, if we have rotated and translated a coordinate frame with respect to another coordinate frame, and in order to represent the pose of the final coordinate frame, we have to multiply a number of these matrices in series in order to represent the final pose of that coordinate frame. Even though previously we have seen a number of applications of the homogeneous transformation matrices, let's look at another example. So here we are given 2 points, PB and QB, and they are to be translated a distance of plus 5 units along XA axis and minus 3 units along the ZA axis. We have to determine the new points PA and QA. So from this question, we can see that First of all, we have a coordinate frame A. So let's draw that. So this is coordinate frame A. Let's label the coordinate frame accordingly. And this will be XA, YA, and ZA. And in the beginning, before translation, we have another coordinate frame B, whose origin coincides with coordinate frame A. So this is XB, and YB over here, it should be parallel and coincide. And this is ZB. And we have points P, B, and QB, which is affixed on the coordinate frame, which means if we translate or rotate the coordinate frame, the points will rotate or translate accordingly as well. So this is affixed on coordinate frame B, but not on coordinate frame A. Now, when the question says we will be translating the points, what we'll be doing really is we will be translating the coordinate frame and hence the points as well. So let's say we have translated the coordinate frame plus 5 units and minus 3 units along ZA, and maybe the coordinate frame will end up here. So this will be the final destination or final location of our coordinate frame B after being translated. So after it has been translated, you can imagine that the point P will be here, PB, and it will be still 432. Okay, but the question wants us to find PA, which means what is this point with respect to coordinate frame A. Alright, and there are two ways to solve this problem. One is to directly come up with the homogeneous transformation matrix TBA, and since there's no rotation, the rotation submatrix is simply identity. This is always 0, 0, 0, 1, and the position of this origin with respect to coordinate frame A is 5, 0, minus 3. 5, 0, minus 3. And then in order to find PA, you just have to use this equation, equals to TBA multiply P tilde B. And we know P tilde B is this position vector expressed in homogeneous coordinates. Or we can also solve it by considering these two translations in sequence. Alright, so TBA is equal to the first translation, which is again, there's no rotation, and the translation is just 5 units along XA, 5, 0, 0, 1, and there's a second translation which is along ZA, which means since there's no rotation, the translation along ZA is equivalent to the translation along ZB. So the second homogeneous transformation matrix will be again no rotation, but the translation part will be 0, 0, minus 3. So now if we multiply these two matrices, we would get, and this will be 0, this part will be 0 plus 5. The second row is just this second row, 0, 1, 0, 0. The third row here will be the third row here, 0, 0, 1, minus 3. And the last row is always 0, 0, 0, 1. And as we can see, we obtain the same matrix as compared to the first method. So what is P tilde A? This matrix multiply 4, 3, 2, 1. 4, 3, 2, 1. Why 1? Why we appended 1 is because this position vector has to be expressed in homogeneous coordinates. So if you multiply this, I'm sorry, I have to write the answer here. So the first element will be 4 plus 5, which is 9. The second element is 3. The third element is 2 minus 3, which is minus 1. And then this is 1. So this is not the final answer. The final answer is PA, which is the first 3 elements of this. So 9, 3, minus 1. There we go. So that is our answer, PA. So using the similar approach, you can solve for QA as well. Now it's a good time to talk about the forward kinematics. In the forward kinematics problem, one has to undertake 4 steps, that is, establish coordinate frame, obtain geometric link parameters. We have to then derive the homogeneous transformation matrices for all the links, and finally we have to compute the final homogeneous transformation matrix. So let's say we are given a robot arm like this, and we know that this is joint number 1, this is joint number 2, joint number 3, and joint number 4, and this will be link number 1, this is link 2, link 3, and we have an any factor here. So in the first step, we'll be establishing a coordinate frame for every link that is attached to the link. For example, first of all, we have to establish a coordinate frame that is fixed on the base. So this is coordinate frame 0, and this will be, let's say, x0 and z0. So this coordinate frame is also known as the inertial coordinate frame for the robot arm. It will remain stagnant for the whole operation. Similarly, we have to establish a coordinate frame for link number 1 here. So I'll just use the symbol. So we'll be establishing a coordinate frame 0 that is affixed on link number 1, coordinate frame 1 that is affixed on link 1. We'll be establishing a coordinate frame for link number 2, and so on. And here there'll be a coordinate frame 3, and finally there'll be a coordinate frame here as well. Let's say this is z4 and x4. So as you can see, for an n degree of freedom robot arm, there will be n plus 1 coordinate frames, right? In this case, the degree of freedom of this robot arm is 4, therefore we have 5 coordinate frames, including the base coordinate frame. So 1, 2, 3, 4, 5. So in the first step, we'll be establishing coordinate frames up to n for degree of freedom. And the next step, we have to obtain the geometric link parameters. So as we will see later, in particular, we have to obtain, so these are the geometric link parameters, theta I, which is the joint variable in our case, because we'll be only considering revolute joints, di, ai, and alpha I. So I here refers to link I. So because if we consider this particular robot, because we have 4 degree of freedom, so we'll be having 4 sets of these parameters, right? So n set of parameters as such. So these 2 steps will be carried out using the Danavid-Hartenberg representation that we will learn shortly. So basically, the Danavid-Hartenberg representation involves a set of algorithms to establish the coordinate frames and to obtain the geometric link parameters. And the third step will be to derive the homogeneous transformation matrices for all these coordinate frames using the approaches that we have learned so far.
And finally, the fourth step will be to compute the final homogeneous transformation matrix, which simply involves multiplying the previously obtained homogeneous transformation matrices. So you know that Tn0 is simply equals to multiplying T10, T21 and so on up to Tn minus 1. Before we proceed with establishing the coordinate frames for every link of a robot arm, let's look at a robot called PUMA 560. So this is PUMA 560 robot arm. PUMA is an acronym for Programmable Universal Manipulator for Assembly, and it is released in late 1970s and is considered one of the earliest or one of the first modern industrial robot arms. Even though it's old, it's not used that much anymore these days. We'll be using this PUMA 560 robot arm to study robot kinematics because it has been widely studied and the robot parameters are available for us to use. And if you manage to understand well robot kinematics of PUMA 560, you should be able to understand robot kinematics of other arms as well. Let's investigate the various joints and links of PUMA 560. So if you have MATLAB and if you have the robotics toolbox installed, we can actually simulate the PUMA 560 robot arm. So this is joint number 1, and the axis of rotation is along this invisible line that I'm trying to show you. Basically it's along the z-axis. That is the axis of rotation of joint number 1. This is joint number 1. And we have joint number 2. This is joint number 2, and the axis of rotation is along y-axis. This is joint number 3, which is here, and again the axis of rotation is along y-axis, this y-axis parallel to this y. Let me try to zoom in to show you. So this will be joint number 4 here, and the axis of rotation is this way. We have joint number 5 right here, and this is the axis of rotation. And finally we have joint number 6, which is here, and the axis of rotation is along this line. Now we are ready to establish the coordinate frames for every link of PUMA 560. So this is the algorithm according to the Danavid-Hartenberg representation. So the first step here, so I hope this is not too confusing. So this little window here is will present the algorithm. This is for us to refer to the joints and links, and this is where we establish the coordinate frames. So step number 1, establish base coordinate frame. Establish a right-handed orthonormal coordinate frame. So in our case, it's always right-handed orthonormal coordinate frame. Coordinate frame 0 at the supporting base with Z0 lying along the axis of motion of joint number 1. Alright, and pointing toward the shoulder of the robot arm. So a few things to note here. First of all, this is the supporting base. This is the supporting base, all right. And we have to, in order to establish Z0, we have to look at axis of motion of joint 1. So where is joint 1? This is joint 1, and as we saw in the simulation earlier, the axis of rotation is along this line. Okay, so our Z0 should be along the axis of rotation of joint number 1. So that is why we have our Z0 here. So this is Z0, and it says it has to point towards the shoulder. So preferably we don't want Z0 to pointing downwards, because if that's the case, it will be pointing away from the shoulder. So if you look at PUMA 560, it has left arm and right arm configuration. So in the simulation, like you saw earlier, if I'm not mistaken, that was the right arm configuration, and this is the left arm configuration. So you can imagine this to be your body or your torso. This is your shoulder, this is your shoulder joint, this is your upper arm, elbow joint, lower arm, and your hand. Alright, so this is your Z0, okay, and then it says X0 and Y0 can be conveniently established and are normal to Z0. So it has, you can establish X0 and Y0 accordingly following the right hand rule. Alright, so if you look at this algorithm of step 1, the origin of coordinate frame 0, which is the initial coordinate frame for our robot arm, it can be anywhere along this line. So you can even establish the coordinate frame, the origin to be here, right, or down here. But we put it here for convenience, as we will notice probably later. Alright, so that is the base coordinate frame, X, Y, Z, 0. Alright. Now let's look at step 2, initialize and loop for each I from I equals to 1 up to n minus 1. In our case, n is 6. This is a 6 degree of freedom robot. So we have to perform steps 3 to 6. So this is step 3, 4, 5, 6. So if you look at step 3, we'll be establishing the Z axis. Step 4 will be establishing the origin, and then step 5 X, step 6 Y axis. And if you look at the figure, I've only drawn the X and Z axis simply to avoid confusion and for better clarity. Of course, if you know X and Z, you can simply draw Y. Alright, so let's look at step number 3. Align Z1. So we are looking at I equals to 1. Align Z1 with the axis of motion of joint 2. For robots having a left-right arm configuration like our PUMA 560, Z1 and Z2 are pointing away from the shoulder and the trunk of the robot arm. So once again, in order to establish Z1, we have to look at joint 2. So where is our joint 2? This is joint 2, right? So this is joint 2, and the axis of rotation is along this line. And according to step 3, our Z1 should be pointing away, and it's along this line. Okay? So you can imagine Z1 is a long line from here. It goes to infinity and is pointing that way, away from our shoulder. Okay? Step 4, establish origin of the ith coordinate frame. So we are looking at coordinate frame 1. Locate the origin at the intersection of Z0 and Z1. Okay? So where is Z0? This is Z0. And this is Z1, and the intersection is right here. So this is the origin of coordinate frame 1. Next, step 5, establish X1. So establish X1 as a cross product between Z0 and Z1, and it can be in any direction. Okay, so this is Z0 and this is Z1, cross product of Z0 and Z1. If positive is that way, if it's negative is this way. So we choose X1 to be pointing this way. So there we go. So that is our, step 6, establish Y. It's simply, you can choose Y by such that it obeys the right hand rule. So if this is X and this is Z, and you know the y1 should be pointing downwards. Okay, so there we go. That's the coordinate frame 1. Okay, so we have done till step 6 for I equals to 1. But remember, we have to do for I 2, 3, 4, 5. Okay, so let's look at Z2. Z2, to establish Z2, we have to look at joint number 3. This is joint number 3, right? And its axis of rotation is along this line. So Z2 should be along this line. And it is according to step 3, because our PUMA 560 in this case is left arm configuration, Z2 should be pointing away. So that's why the arrow shows that way. So this is our Z2. Step number 4, establish the origin. Is the intersection of Z1 and Z2. So this is Z1 and this is Z2. So there's no intersection, right? Because Z1 is parallel with Z2. But look at here, it says or at the intersection of common normal between Z1 and Z2. We find the common normal and the intersection of that with Z2. So common normal is a line that is perpendicular to both Z1 and Z2. So if we just focus on Z1 and Z2, common normal, we have infinitely many line that is normal or 90 degrees perpendicular to both Z1 and Z2. Okay, so we choose one and find the intersection between that common normal with Z2. So once again, so this is my Z2. Because Z1 and Z2 is parallel, we have to choose a common normal. So imagine I choose a line, this line, right? So this line is perpendicular to both Z1 and Z2, okay? So that is my common normal. So where is the intersection of my chosen common normal with Z2? So it's exactly at this point right here. So that is my origin. Okay. Step number 5, we have to establish X2. Because once again, because Z1 and Z2 is parallel with each other, X2 is the common normal, the chosen common normal, okay? So remember, I chose this is my common normal. So this is my X2, right? So there we go. We have established coordinate frame 2. How about coordinate frame 3? Once again, we have to look at joint 4. So this is my joint 4, right? Joint 4, and the axis of rotation is along this line. Okay, so we can imagine my Z3 is along this line. So I chose my Z3 to be pointing this direction, okay, because well, it doesn't impose any condition where it should be pointing for Z3. So I chose Z3 to be pointing this way. All right. Next, step 4, we have to find the origin. Okay. There's no intersection because Z3 is higher than Z2. But again, if there's no intersection, we have to find the common normal. Okay. So the common normal between of Z2 and Z3, you can choose this line, right? This line right here, and the intersection of this line with Z3 is right at this point. So that is my origin, right? And then my X3 is just the common normal, which is this line. This is my X3. Next, let's move to coordinate frame 4. Coordinate frame 4, we have to look at joint number 5. Where is joint number 5? This is joint number 5, right? And the axis of rotation is along this line. Okay, so that's why Z4 is along this line. It's pointing that way. This is Z4. What is next? We have to locate the origin of coordinate frame 4. It is the intersection between Z3 and Z4. It is at this point. Alright. So next, X4 is the cross product between Z3 and Z4. It can be positive or minus. So if we take Z3 and Z4, we find the cross product. We find X4 to be either downwards or upwards. So we chose downwards. So this is my X4. Next, let's look at coordinate frame 5. In order to establish coordinate frame 5, we have to look at joint number 6. So this is joint number 6 right here, and the axis of rotation is along this line. So Z5 is pointing this way. Okay. So the origin of coordinate frame 5 is the intersection between Z4 and Z5 is at this point, right? And the X5 is the cross product between Z4 and Z5. You take cross products of between Z4 and Z5, we have X5 this way. Right? This is our X5. So if we briefly look at step number 2, we have to do that up to n-1, up to I equals to 5, right? So we have established coordinate frame 5. Now let's move on to step number 7. Establish hand coordinate frame. So this is the last coordinate frame, and it is usually on the n effector. So it says usually nth joint is a rotary joint, okay, which is true in our case, and establish Zn along the direction of Zn-1. So we have to establish Z6 along the direction of Z5. So this is our Z6. I've drawn it to be the same line. So this line represents Z5 and Z6. And pointing away from the robot, which is true, okay, establish X6 such that it's normal to both Z5 and Z6. So I can choose anywhere, the origin to be anywhere. So it can be either at the end of the tip or in the middle of the end effector. So this is our origin of the last coordinate frame 6, and X6 is parallel to both Z5 and Z6. So this is how it looks, X6. And then finally assign Y6 to complete the right-handed coordinate frame. Alright, now that we have developed or established coordinate frames for every link for our PUMA 560, let's try to come up with the geometric link parameters. Like I said earlier, we will be finding out what are the theta i's, di's, ai's, and alpha i's. So these parameters are also known as the DH parameters. So for theta I, first of all, we have to find 6 sets of these parameters because we have 6 joints. So for theta, we will just leave it as a variable, theta 1 up to theta 6. The reason for this is because these are our joint variables, because we have only revolute or rotary joints for our PUMA 560 robot. And for a given different pose of different poses of our end effector with respect to the base coordinate frame or different configuration, we'll be having different values of these thetas. So during operation, we have to substitute those actual angle values here in order to compute the homogeneous transformation matrices. But for now, to find the DH parameters, we can just leave the thetas to be as theta 1 up to theta 6. Now what is DI? So in order to find these parameters, first we have to rotate. Let's say, so now we want to find out what is D1. This is D1. D1. So how much? First we have to rotate coordinate frame 0 about Z0 such that X0 and X1 are in parallel. So as we can see now, X0 and X1 are not in parallel. So let's rotate coordinate frame 0 about Z0 to make X0 and X1 in parallel. So let me draw the coordinate frames roughly. So we have this is X1 and this is Z1. So after rotation we would have this. So this is Z0 and this is X0. Okay, so we have rotated at an angle, doesn't matter what is the angle, and our job, the main objective now is to make X0 and X1 in parallel. Okay, the origin can be different, but it has to be pointing in the same direction. Not only parallel, but it has to be pointing in the same direction. So once we have done this, to find D1, we need to ask ourselves how much we have to translate coordinate frame 0 in Z0 to make X0 and X1 to be in the same line. Okay, so because they are already in the same line, so we don't have to translate in Z0, so therefore D1 is 0. Okay, next, to find A1, how much I have to translate coordinate frame 0, this coordinate frame, in X1 to make the two origins coincide. Fortunately for us, for this particular case, the origins have already coincided. So therefore, we don't have to translate in X1. Therefore, A1 is 0. Okay? And the next question, to find alpha 1, how much I have to rotate coordinate frame 0 about X1, Xi, right? I is 1, X1, such that to make the two coordinate frames coincide. As you can see, they are not coinciding now because Z0 is pointing upwards and Z1 is pointing this way. Therefore, in order to make the two coordinate frames coincide, I have to rotate coordinate frame 0 minus 90 degrees about X1. Okay, so if I rotate this minus 90 degree, then I will end up having Z0 over here. Okay, then the two origins, the two coordinate frames coincide. They'll be exactly the same. Okay, so that is why alpha 1 is minus 90 degrees. Alright, so that is just the first set of DH parameters for joint 1. How about joint 2? So let me just erase all this. So I want to find what is D2. So the same thing, we have to, first of all, so this is my coordinate frame 2. So let me just redraw that. So my Z2 is pointing this way and my X2 is pointing this way. Okay, where is X1? This is X1, X1 and Z1. So first thing we have to do, I have to rotate about Z1 such that X1 and X2 are pointing in the same direction, parallel and pointing in the same direction. Okay, so it seems like I don't have to rotate because they are already pointing in the same direction. Alright, next, to find D2, I need to ask how much I have to translate this coordinate frame in Z1 to make X1 and X2 in the same line. So as you can see, right, I have to move from here up to here, right? This is my coordinate frame 2. I have to move from here to here, right? So therefore this is D2. And fortunately for us, because we know the specification of PUMA 560 fairly well. We know that D2 is 149.09. Okay. Next, so you have to imagine that the coordinate frame is over here, right? Let me just, so it's here. Let me use another color maybe. So this is Z1 and X1 is this way. Next, number 3, we have to find now A2. So how much, to find A2, how much I have to translate this coordinate frame in X2, okay, to make the two origins coincide, these two origins, right? How to make them the same, coincide. So we have to move this much, okay, this much. So this is A2. And A2 we know from our specification of the robot, A2 is 431.8. So you have to imagine we have translated, and now this coordinate frame appear to be here, right? So this is X1 and this is, sorry for my drawing, this is my Z1. Next, to find alpha 2, how much I have to rotate about X2 to make the two coordinate frames coincide? The answer is 0. I don't have to rotate them because they have already they are already the same, right? So 0 degrees. Okay. Now let's move on to joint number 3. So let's look at coordinate frame 3, which is up here, right? Slightly up here. All right. So so the first step. So now I want to find D3. So first thing, we have to rotate about Z2 such that X2 and X3 is pointing in the same direction. Okay, so let me just try to draw it again. So I'll draw my X3 and Z3. So this is Z3 and this will be my X3. So I know my Z2 is down here, right? So if how much, in order to find D3, first I have to rotate coordinate frame 2 about Z2 to make X2 and X3 pointing in the same direction. Okay, so let me use another color. So my Z2 remains here. So I have to rotate this coordinate frame with respect to Z2 and to make these two pointing the same direction, right? So this is my X2. Okay. Next, how much? So now we can find D3. How much I have to translate coordinate frame 2 in Z2, right? To make them to make them to be to make X2 and X3 to be on the same line. Okay, they are already on the same line, so I don't have to translate this coordinate frame on in Z2. So D3 is 0. Okay. Next, we want to find A3. A3, now we have to look at X3. The question is how much I have to translate coordinate frame 2, which I have rotated and translated, in X3 to make the two origins coincide. Right? Look at this. Here, first we make them pointing the same direction. Next, we make them to be on the same line. And the third step, we have to make the origins coincide. So from here, you can see that we have to move up in the negative direction, right? Because we are referring to X3. Okay, so that is why, as you can see a little sign label here, it says this is A3. All right, so it should be this one, but yeah, it's drawn in perspective. So this is A3 right here, and A3 is minus 20.32. Okay, so after moving it, you can imagine my coordinate frame 2 appears up here because we have moved backwards, right? Minus 20.32, that is A3. So this is my X2. Next, how much I have to rotate coordinate frame 2, the latest one, about X3 to make the two origins coincide. So in order to make the two origins coincide, Z2 will have to be here, right? And that is positive 90 degrees. Here, positive 90 degrees. That is my alpha 3. Okay? Should I explain further? Alright, let's try to find everything today. Let's move on to the fourth join. So we have to look at coordinate frame 3 and coordinate frame 4. So this is my coordinate frame 4, right? And this is my coordinate frame 3. So first step, I want to find D4. And before that, we have to ask ourselves how much I have to rotate this coordinate frame 3 about Z3 to make X3 and X4 pointing in the same direction, right? And the answer is they are already pointing in the same direction, so I don't have to rotate. Next, how much I have to translate coordinate frame 3 in Z3 to make X3 and X4 in the same line, to be in the same line. The answer is this much, right? From here, I have to move up to here. Only then X3 and X4 will be on the same line. And this distance is given by here, it's labeled here D4, and from our dimensions of the PUMA 560, we know it's 433.07. Alright, so now we have to imagine that we have our Z3 pointing this way. So let me just draw for clarity. Okay, so this is now we have found our D4. This is Z4, X4, and we have Z3 over here. And X3 pointing downwards. Okay, so next, how much I have to translate. So I want to find A4, how much I have to translate coordinate frame 3 in X4 to make the two origins coincide. Right, the answer is 0. I don't have to translate because they are already the same point, 0. And then finally, how much I have to rotate coordinate frame 3 about X4, right? Such that the two coordinate frames coincide. So the answer is minus 90 degrees. From here, I have to rotate this way. Okay, so that's why alpha 4 is minus 90. All right, let's erase this. Now, fifth join. It should be quite simple because it seems like coordinate frame, the origin of coordinate frame 4 and 5, they seem to be coinciding, or it's the same origin. So how much? First, we want to find D5. We have to rotate coordinate frame 4 about Z4 such that X4 and X5 is pointing in the same direction. Okay, we don't have to rotate because they are already pointing the same direction. Next, how much to translate coordinate frame 4 in Z4 such that X4 and X5 are on the same line? The answer is 0. They are already on the same line. So that is why D5 is 0. Okay, next, how we want to find A5. How much to translate coordinate frame 4, okay, coordinate frame 4 in X5 such that the two origins coincide. Okay, the two origins are already at the same point, right? So A5 is 0. And how much we have to rotate coordinate frame 4 in x5 so that the two coordinate frames coincide. Okay, let's see. This is z5, right? This is z4. So the question is, we want to find alpha 5. So alpha 5 is how much we need to rotate coordinate frame 4 about x5. So this is x5. So we look at here, we look in this direction. We know that from here we have to rotate 90 degrees, right? So that is why alpha 5 is 90 degrees. Finally, you have to take note that the origin of coordinate frame 6 is right here, right? This point here is not here. So here, first step, let's rotate coordinate frame 5 about z5, I minus 1, z5, such that x5 and x6 pointing in the same direction. So we don't have to rotate because x5 and x6 both are pointing downwards. Next, d6 is how much we have to translate coordinate frame 5, right, I minus 1, right, in z5 such that both of x5 and x6 are on the same line. Okay, so this is x5, this is x6, this is z5. So I have to move this much, right, in order to make x5 and x6 to be on the same line. Okay, so this is 56.25. All right, this much from here to here. Okay, from here to here. So next, we want to find A6. A6 is how much I have to translate coordinate frame 5, which we have rotated and translated. How much we have to translate again in x6 such that the two origins coincide. So we have just moved from here to here, and the origins are coinciding already. Okay, so we don't have to translate in x6. So that is why A5 is 0. Okay, and imagine now coordinate frame 5 is here. So z5 is pointing in the same direction as z6. x5 is the same direction as x6. So we don't have to rotate coordinate frame 5 about x6 to make them the same. So that is why alpha 6 is 0 degrees. Okay, I hope that's clear. Now let's look at another robot, the PUMA 260, and see how we can establish the coordinate frames and obtain the geometric link parameters according to the Danavid-Hartenberg representation. So here we are given some indications of the joints. So this is the axis of rotation of joint number 1. So joint number 1 should be somewhere around here. And this is the axis of rotation of joint number 2. This should be joint 2. And this is axis of rotation of joint number 3. This is the axis of rotation of joint number 4. And this is joint 4. This is joint 5. And this is the axis of rotation of joint 5. And here we have joint number 6 and its axis of rotation. So the first step in establishing coordinate frames for every link of the robot arm is to establish coordinate frame 0, which is the base coordinate frame, and is also the inertial coordinate frame. And since we have 1, 2, 3, 4, 5, 6 joints, hence this is a 6 degree of freedom robotic arm. Therefore we should establish 6 plus 1 coordinate frames. So the first one will be the base coordinate frame, and according to the algorithm, Z0 should be along the axis of rotation of joint number 1. So this is the axis of rotation, and as you can see, the base coordinate frame has already been established for us. So this is Z0, and X0 and Y0 can be arbitrarily assigned as long as the coordinate frame obeys the right hand rule. Also, according to the algorithm, theoretically we can set the origin to be anywhere along this line. However, we don't have the physical robot in front of us, we only have this figure, so it's a good idea to set the origin of the base coordinate frame 0 to be here, because we are given this dimension. And in the future, in the next step, this dimension will be helpful for us to determine probably D1. If we establish the origin to be here, then we wouldn't know the distance from here to here. So we'll be having a problem in determining what is D1. Anyway, let's find the next coordinate frame 1. And according to the algorithm, Z1 should be along the axis of rotation of joint 2. So this is the axis of rotation of joint 2. So here we have established all the coordinate frames. Let's see how did we get this. So this is Z1, okay, and according to the algorithm, the sequence is we have to determine Z-axis, the origin, X-axis, and then Y. So this is Z1. And next, what is the origin? The origin is the intersection between Z0 and Z1. So if we extend Z0, and this is Z1, the intersection is at this point, the yellow circle. So this is the origin of coordinate frame 1. And X1 is the cross product, plus or minus, between Z0 and Z1. So we choose this direction. And this is Y1 according to the right hand rule. Next, Z2 has to be along the axis of rotation of joint number 3. Right? What is the origin? The origin is, because Z1 and Z2 is parallel, we have to find a common normal between Z1 and Z2. Let's imagine there's a line here. So that is the common normal, and the origin is the intersection of the common normal with Z2. So this point right here, right? And X2 is just the common normal we have here. Next, coordinate frame 3. It has to be, Z3 has to be along the axis of rotation of joint number 4. So this is joint number 4, and this is the axis of rotation, therefore this is Z3. Alright, so if we extend Z2, we can see this is the intersection. So that is the origin of coordinate frame 3, and the cross product between Z2 and Z3 can be this direction or upwards. So we choose downwards. So this is X3. Next, Z4. It's along the axis of rotation of joint number 5. So this is joint 5, and this is Z4. Again, we can extend X3 and find the intersection between Z3 and Z4, which is this point, and the cross product between Z3 Z4 is this direction, can be this downwards or upwards. So we choose downwards. And how about coordinate frame 5? We have to look at joint number 6. So this is joint 6. So this is Z5, right? What is the origin of coordinate frame 5? Is the intersection between Z4 and Z5, which is here. This the same origin as before. And the cross X5 can be plus or minus cross product between Z4 and Z5, and as we can see, we chose this one. And Z6, the last one, according to the algorithm, this is the hand coordinate frame. We don't have an end effector here, but still it says that Zn has to be in the same direction as Z5, so that's why Z5 and Z6 is the same direction, and X6 should be perpendicular to both Z5 and Z6, so we choose here, and the origin we choose to be at the end or at the tip of our link 6, right? And then we have our Y6 according to the right hand rule. So there we go, we have established the coordinate frame for every link for PUMA 260. Next, let's look at how to obtain the DH parameters. So these are the DH parameters for PUMA 260. Let's see how did we obtain this. So like before, all these joints are revolute joints or rotary joints. Therefore, these are our joint variables. So we leave it as a variable from theta 1 up to theta 6. Let's find D1. So D1, first we have to rotate coordinate frame 0 about Z0 to make X0 and X1 pointing the same direction. So they are pointing the same direction already. Next, we have to translate coordinate frame 0 in Z0 such that X0 and X1 are in the same line, on the same line. So, so that is D1. So as we can see from here, we have to translate this much, right, in order to make X0 and X1 to be in the same line. So D1 is 13 inches as given here, right? So you can imagine this coordinate frame has gone up here with Z0 pointing upwards and X0 pointing here. Next, how much we have to translate in X1 such that to make the origins coincide. That is A1, right? And as you can see, when we moved this up here, the origins have already coincided. Therefore, A1 is 0. Okay. So again, imagine this is we have Z0 here, we have X0 here. Next, how much we have to rotate about X1 to make the two coordinate frames coincide. And as you can see, probably in your mind, in your head, we have to rotate minus 90 degrees, right? We have to rotate so that Z0 from here will end up to be parallel and coincide with Z1. Okay, so that's why alpha 1 is minus 90 degrees. All right, next, let's look at joint number 2. So this is the coordinate frame 2. Now maybe should I draw? Let's see if we can do this without drawing. Okay, so first, what is we have to rotate coordinate frame 1 so that to make x1 and x2 pointing in the same direction. They are already pointing in the same direction, so we don't have to rotate. Next step, in order to find D2, we have to ask ourselves, so D2 is how much we have to translate this coordinate frame in this direction such that these two are on the same line, right? And as you can see, they are already on the same line, so D2 is 0. We don't have to translate. And what is A2? A2 is the question, A2 is how much we have to translate this coordinate frame in with respect to on x2, on this axis, to make the two origins coincide. And the answer is we have to translate from here to here, right? 8 inches. So 8. So now you can imagine we have this coordinate frame to be here already, and how much we have to rotate coordinate frame 1 about x2 to make the two coordinate frames coincide. The answer is 0 because they are already the same, right? So alpha 2 is 0. Alright, let's look at coordinate frame 3, which is over here. Perhaps it's a good time for me to draw for better understanding. First question, how much, so we have to rotate this coordinate frame about z2 to make x2 and x3 pointing the same direction. Okay, so let me briefly try to draw here. So we are looking at joint number 3, so this is z3 and x3 is pointing downwards. This is x3. So let's rotate first. So after rotation, to make x2 and x3 pointing the same direction, I would have this, right? So z2 remains the same because we rotate about z2, and now x2 is pointing downwards. Okay, so in order to find D3 is how much I have to translate this coordinate frame in Z2 so that X2 and X3 on the same line. Okay, so obviously the answer will be negative, right? So I have to translate from here to here. Okay, and it's written here minus D3 because from the figure the dimensions are not given, so we don't know how far is it from here to here. So for this particular example, we just write minus d3, okay, from here to here. And why minus? Because look at this, right? Because d3 is how much we have to translate in z2. So because we have to translate in the opposite direction of z2, therefore it's minus. All right, so now our coordinate frame would be here because we have just translated. So this is z2 and x2 will be here. So we want to find a3. All right, so a3 is how much we have to translate coordinate frame 2 in x3 to make the origins coincide. The origins already the same. The origins are already the same, right? So we don't have to translate. A3 is 0. Next, how much to find alpha 3? How much I have to rotate coordinate frame 2 about x3? And the answer is we have to rotate from here to here, right? And this is 90 degrees. So therefore, alpha 3 is 90 degrees. And similarly, you can derive how did we get the other parameters yourself. So I leave it as an exercise for you to try. So as we have talked about earlier, in forward kinematics, one has to carry out a number of steps. First, we have to establish coordinate frames for every link of a robot arm. Next, we have to find the geometric link parameters. So the first two steps, we have to follow the DH representation. And the third step will be to find homogeneous transformation matrices representing the pose of coordinate frame I with respect to coordinate frame I minus 1. So earlier, when we were finding the DH parameters, if you realize, we were performing a series of rotations and translations. Namely, we were rotating coordinate frame I minus 1 with respect to about zi minus 1, and then we were translating in zi minus 1, and then again we were translating in xi, and then finally we rotated about xi. So if you realized what we were doing, really, we were bringing coordinate frame I minus 1 to become coordinate frame I. Or in other words, we were rotating and translating such that coordinate frame I minus 1 will be coinciding with coordinate frame I. So therefore, in order to find the homogeneous transformation matrix representing the pose of coordinate frame I with respect to coordinate frame I minus 1, we can simply multiply a series of homogeneous transformation matrices representing those rotations and translations. So the first homogeneous transformation matrix is is this one, which is rotation about z-axis. This is translation in z-axis. This is translation in x-axis, and this is rotation in x-axis. So when we multiply these four matrices together, we will end up with ti I minus 1 as given by this. And as we can see, this matrix is in terms of variables, right? So next, we can just substitute our dh parameters in this matrix. For example, if we want to have t1 is 0, so we just substitute these values right here for the joint number 1. So di13 you substitute here, ai you substitute to be this, and so on. But theta, we leave it as a variable because theta depends on the configuration of the robot, whereas di, ai, and alpha I are constants because that depends on the coordinate frame that we have established, and normally we won't change our coordinate frames. So once we have obtained that, we can just multiply these matrices together to get T60, for example. All right. So using the Ti I minus 1 matrix, we can relate a point Pi at rest in link I and expressed in homogeneous coordinates with respect to coordinate frame I to the coordinate frame I minus 1 established at link I minus 1 by this formula. So this is the formula that we have seen earlier. So usually we are not interested in T10, mapping a point from one link to another, but we are more interested in mapping the n effector to the base coordinate frame. So therefore we'll be multiplying the 6 matrices together to find T60. So the 6 homogeneous transformation matrices for the 6-axis PUMA 560, we have found it, and is given by these matrices. So as you can see, we have substituted the di, ai, and alpha I values, but we have left the theta i's as variables. So here C1 is an abbreviation for cos of theta 1, and Si stands for sine of theta 1. So this is T10 up to T65. So in order to obtain T30, we just multiply 1, 2, 3 matrices, and T63 we multiply 1, 2, 3 matrices, and in order to find T60 we just multiply this matrix with this matrix. Okay, so let's look at a simple example. So it says here, as a check, if theta 1 is 90 degrees, theta 2 is 0 degrees, and so on, then the T matrix is given by this. So please try this as an exercise. So you know that you can obtain this by substituting these values into these two matrices, and then you multiply these two matrices together in order to obtain T60. Okay, it says that this matrix now agrees with the coordinate frames that we have established in figure 2. So namely, you should be able to validate that the pose of coordinate frame 6 should be as given by this matrix with respect to the coordinate frame 0. For example, we will be able to see that x6 is in the negative direction of z0. Right, let's see, x6, is it minus z0? So this is x6, right, it's pointing downwards, and z0 is pointing upwards, okay, which is correct. And similarly, you can try to verify the other axis and the position vector as well. Now that we are done with the forward kinematics problem, let's talk about the inverse kinematics problem. So in the inverse kinematics problem, given the position and orientation of the end effector of a 6-axis robot arm as T60 and the geometric link parameters or the DH parameters, we would like to find the corresponding joint angles θ1 up to θ6 of the robot so that the end effector can be positioned as desired. Now, can you think of an application of the inverse kinematics problem, or why is it important that we study this? So for the PUMA robot arm shown in figure 2 that we saw earlier, various arm configurations are defined according to human arm geometry and the link coordinate frames which are established. We have right arm, left arm, above arm and below arm. So if you remember in the animation, it was a PUMA 560, but the configuration is right arm. And in figure 2, we saw left arm. So according to the definition of left arm configuration, it says positive θ2 moves the wrist in the negative ZO direction. So let's look at figure 2, positive θ2, negative ZO. So this is figure 2. So positive θ2, indeed, it moves the wrist in the negative ZO direction. ZO or Z0 is pointing upwards. When we have positive θ2, the wrist moves downwards or in the negative direction of Z0. And similarly, you can analyze for right arm as well. So next configuration, we have the above and below arm. All right, if you look at these figures, so this is left and left, but this is left and above, and this is left and below. So it's pretty obvious what is above arm and below arm, but I want you to still pay attention on the definition. It says above arm is position of the wrist of left arm, for example, has positive coordinate value along y2 axis. So once again, if it has an above arm configuration, position of the wrist of left arm has positive coordinate value along y2 axis. Okay, let's see above arm. So where is y2? So if you cross check with figure 2, y2 axis is pointing downwards, right, perpendicular to this link. So if this is y2, and what is the position of the wrist? Indeed, it is positive y2 because y2 is pointing downwards. This is the position of the wrist. It is positive y2. And how about below arm? This is below arm. Where is y2? y2 is pointing this way. This is the positive direction. This is the negative part of y2. Now the position of the wrist is indeed negative y2. So what if the arm is straight? Is it above arm or below arm? So please discuss about that. So with respect to the above definition of various arm configurations, we have two configuration indicators, or these are variables that will appear in our inverse kinematics equations later. So for the arm indicator has positive value for right arm, negative value for left arm, and the elbow indicator is positive for above arm and is negative for below arm. We have to define a new position vector called P, and this is P equals to P6 minus D6 multiply A. So where is P? So once again, if you cross-check with figure 2 of our PUMA 560 robot arm, this is joint number 4 and this is joint number 5. This is joint number 6. Alright, so the axis of rotation of Joint number 4 is this line here, and the axis of rotation of joint number 5 is this line, and the axis of rotation of joint number 6 is this line. So P is the position where these three axes of rotation coincides. So we'll be using this point in the derivation of our inverse kinematics equation. And as we can see, P from vector notations, right? So P equals to P6 minus D6 multiply A. So what is P6? P6 is the position of the origin of coordinate frame 6, the last coordinate frame, which is on the end effector, right? A here is a vector. We call it approach vector in the robotic arm convention. So this is slide vector S, this is approach, and this is normal. But we know from our establishment of coordinate frames according to the DH representation, this is X. So A is the third column of our homogeneous transformation matrix T60. Okay. So and then D6 is from our DH parameter, all right? D6 is from our DH parameter. So if you recall, D6 is the distance between coordinate frame 5 and coordinate frame 6. So we'll be using Px, Py, Pz, which are the components of P in the later equations. So if we project the position vector P, which we have just defined, this one, right, or this one, onto x0, y0 plane. So this is part of our base coordinate frame, or coordinate frame 0. We will have this figure. If we project it on that plane, we have this figure, and we can see OA. Again, you can compare this with figure 2 for better understanding. OA is D2. D2 is one of the DH parameters, and this is the distance between coordinate frame 1 and coordinate frame 2. Or in other words, how much we have to move in Z1 such that X1 and X2 are on the same line, if you remember, right? So that is D2. And OB is simply, this is our point P, right? So because we have projected on x0, y0, this point is Px, Py, Px, Py, here, right? So OB is Px squared plus Py squared, square root the whole thing. And AB, this is according to the Pythagoras theorem, this length minus the square root of, yeah, you know the math, right? So this this squared plus this squared is this squared, right? So that's why AB is given by this equation, and we call it R, small r. So OB is capital R. So all this we'll be using later. And similarly, we can analyze the same for right arm configuration. And after moving things around, long story short, we end up with this equation. So this is the solution for joint number 1, the angle theta 1. So even though practically, in practical applications, we have to compute theta 1 up to theta 6 for every desired configuration of your robot arm, in our interest, we will be only looking at theta 1, theta 2, and theta 3. So in order to compute theta 1, we need R, and in order to compute R, we need D2. So to compute theta 1 from our DH parameters, it seems like we need to have D2 and also D6. And this is the equation for theta 2. It gets slightly more complicated, and we need more parameters from our DH parameter table. We need to know D4, D2, D6, because we needed to compute P. We need A2, A3, right? And this is theta 3. Again, we need some parameters from we need a number of DH parameters as well. So let's look at this example, right? So if you notice, this matrix from the previous example is the same. So this is T60. This is the pose of our n effector of PUMA 560 with respect to the base coordinate frame. So you can view this as the desired configuration of our robot arm, or the desired pose of the end effector of PUMA 560. And using inverse kinematics, we can compute for theta 1, theta 2, theta 3, up to theta 6 really, that would result in this desired configuration. Let's see how we can solve this. So we are given T60. This is the homogeneous transformation matrix representing the end effector of the PUMA 560 robot as shown in figure 12 with respect to the base coordinate frame. And these are the equations to find theta 1 according to the inverse kinematics. So as you can see, to solve for theta 1, we would require some parameters from the DH parameter table of PUMA 560. So we need D2. So from table 1, it is 149.09. We need D6 because we need to compute P, right? Here R requires Px, Py, and this is P, and P equals to P6 minus D6. So this is from the DH parameters A. So what is P6? P6 is the position vector of the origin of our coordinate frame 6. Alright, so this is P6. As you can see, A is the, as I've explained earlier, is the approach vector of coordinate frame 6. So it is 0, 1, 0. So you can see here 0, 1, 0. So we have computed Px, Py, Pz to be this. So using these values and D2, we can compute R. It is 864.87. Tangent theta 1 is arctangent of a numerator term and the denominator term, which are given by this. So in these equations, we have the indicator arm, and I've used arm to be minus 1. So find out why I used arm to be minus 1. Okay, that is your task to find out. So we substitute Py from here to here, R from here to here, and Px as given by this. We get a positive number. At this point, it doesn't matter because the denominator is 0 if you compute it. So arctangent of a positive number over 0, which is positive infinity, theta 1 is 90 degrees. Okay, so please find out. So two things for you to find out: why I used arm to be minus 1 and why this leads to 90 degrees. Alright, next question, theta 2. So these are the equations for theta 2. Some of the terms that we have to find in order to compute theta 2. So we have to compute R, C alpha, this is cos alpha, sin alpha, cos beta, sin beta, and then sin theta 2, cos theta 2, and finally theta 2 equals to arctangent of sin theta 2 over cos theta 2. And if you go through these equations and the variables, you will realize that we would need D2, D4, A2, A3 from the DH parameter table, table 1. We also require the p-value that we have computed earlier. So I just write it here for reference. And arm indicator is again, is -1. And we need to have, we need to know the elbow indicator. Again, is -1. So why it's -1? Your job to find out, right? So by substituting the p-value and D2, we can compute R. So we have 865.1087, cos alpha 0.9997. So please make sure in your calculation you write up to like maybe 4 decimal places for accuracy. And sine theta, we obtain minus 0.0235. And then cos beta, it's the same as this, coincidentally. Sine beta is just the square root of 1 minus cos beta squared. And we obtain 0.0235. Next, sine theta 2, we get 0. And cos theta 2, we get a positive number. So again, I don't care what is exactly the number, because I know tangent inverse of 0 over positive number is inverse tangent 0, which means theta 2 is 0 degrees. Okay, that's pretty straightforward. So we have solved for theta 1 and theta 2. Let's look at theta 3. So again, these are the equations that we have to solve for theta 3. At the end, theta 3 equals to arctangent of sine theta 3 over cos theta 3. And in order to arrive at this, we have to compute cos phi, sine phi, cos beta, sine beta. And if you go through the variables that I used, we need D4, A2, A3, R, which we have computed earlier for theta 2. And again, we need arm and elbow. Okay. So cos phi, I found it to be minus 0.9989. Sine phi and cos beta are the same, 0.0469. Sine beta 0.9989 is just the minus of cos phi, coincidentally. Cos theta 3 is 0 and sine theta 3 a positive number. And theta 3 is inverse tangent of sine theta 3, which is a positive number, over 0. So this is infinity, and therefore theta 3 is 90 degrees.